I'm Tomohiko Kumagai from Meiji University, Japan. In this study, Elasto-plastic seismic response behavior and evaluation of permissible deformation of single-layer lattice domes design and various laws are investigated. Contents of this study are shown here. This study consists of these 7 chapters. Several studies have been made on the response behavior of the single-layer lattice structures subjected to earthquake motions. However, there are no previous studies with dealing about the evaluation of the permissible plastic deformation of the spatial structures subjected to earthquake motions except for our study. In addition, the effects of design laws for spatial structures on the permissible plastic deformation are not made clear. Therefore, the elasto-plastic dynamic response behavior of the single-layer lattice domes designed under dead load only or under dead load plus snow load subjected to earthquake motions in the horizontal and the vertical directions is investigated by numerical analysis. In addition, the permissible plastic deformations of domes are evaluated by focusing attention on the nodal rotations and the rotational angles at the center of members. At first, I show you the outline of numerical analysis. The analysis models are rigidly joined single-layer lattice domes with substructure, as shown here. The shape of the geometrical initial imperfection are similar shape to eigenmodes with large effective mass of domes without imperfection. The maximum amplitude of the imperfection are set for 0.2 by equivalent shell thickness TE. The names of analysis models are defined as shown here. The mass ratio Rm are obtained and the ratio of the mass of substructure to that of roof structure. The natural period ratio Rt is adjusted to 1.0. Methods of analysis are a natural vibrational analysis and dynamic response analysis, which takes into account the geometrical and material nonlinearities. The input earthquake ground motions are the simulated earthquake motion with phase characteristics of El Centro and Taft, and observed earthquake motion El Centro NS and UD. In determining the collapse accelerations of lattice domes, the maximum plastic rotation angle θ PL max is defined. The definitions for the rotational angles at center of member and the nodal rotation angles are shown in figure. Right figures show the definitions for the plastic rotation angles θ PL. The plastic rotation angles are obtained by skeleton curve. θ PL max is taken as the maximum value of all members of dome roof. Figure shows correspondence relationships between the seismic intensity equivalent to the collapse acceleration determined by the Bryansky loss method and the seismic intensity lambda E when the maximum plastic rotation angle exceeds 0.04 radian or 0.08 radian in the previous studies. At 0.04 radian, there is some variation in the correspondence. On the other hand, at 0.08 radian, the variation is smaller. Therefore, in this study, the input when the maximum plastic rotation angle reaches 0.08 radian are defined as a collapse acceleration. Next, the relationships between maximum plastic rotation angles and the input accelerations are investigated. In the model with HS equals 0.0 meter, the rotational angles increase rapidly after the collapse, On the other hand, at the HS equals 0.6 meter, the rotational angles increases as the input accelerations increases. It cannot be said that the unified behavior appears depending on HS, the shape of initial imperfection, and the mass of the substructure. Therefore, a new indicator is introduced. The relationships between plastic rotation angle and the structural instability are examined. In this chapter, we introduce the product of the sum of the plastic rotation angles of the member of dome roof, sigma theta PL, and the plasticity ratio RPL member. Figures show the relationships between the input accelerations and the average value of the plastic rotation angles. As the input acceleration increases, the rate of increase in the average value of the plastic rotation angles gradually increases. From this, it is considered that the structural instability phenomenon will not occur immediately in the dome if this rate of increase can be suppressed to a certain value or less. Therefore, as shown in figure, keeping the rate of increase of sigma theta PL RPL member relative to input accelerations smaller than the permissible slope S bar obtained by the second line are considered. Here the point where the permissible slope and the rate of increase of sigma theta PL RPL member relative to input acceleration intersect is defined as the permissible average plastic rotation angle. Figure shows the relationships between the permissible average plastic rotation angle and the product of the coefficient. This product is introduced for the evaluation of permissible deformation. This product is obtained from the shell-like factor Xi0, safety factor nu, and the response amplification factor Fv'. As the product of the coefficient increases, the permissible plastic rotation angles decreases. The permissible plastic rotational angle is about 0.03 radian for the dome with perfect shape, and about 0.07 radian for the dome with imperfection. Figure shows the relationships between the maximum vertical displacement at a permissible average plastic rotation angle and the product of coefficients. By considering the imperfections, the difference due to the seismic waves are reduced. The permissible plastic deformation decreases, the product of the coefficient increases. The permissible deformation of the dome targeted in this study is 1/600 to 1/300. Summary of results obtained are shown here. Thank you very much for your kind attention.